This will be the first of 3 lectures on the cardiovascular responses to exercise. We'll be talking in this first part about the cardiac output and factors that determine cardiac output. First of all, what is cardiac output? It's the amount of blood that is pumped from the heart each minute. It can be abbreviated capital C, capital O for cardiac output, or, which is still more common even though it's more old-fashioned, Q subscript C. Now the Q is usually shown with a dot over it. The dot tells you it's a rate, but I'm not very good at putting a dot in these presentations, so you just have to imagine, and on your handouts you can put a dot over the Q, Q subscript C, cardiac output, the amount of blood pumped per minute. The second bullet here shows you the relationship that mathematically determines your cardiac output. Cardiac output is the product of heart rate and stroke volume. Cardiac output equals heart rate times stroke volume. Heart rate, you know, is the number of heartbeats, the number of times the heart pumps, contracts each minute. Number of contractions per minute. Stroke volume is the amount of blood pumped in each of these beats. So the product, how many beats there are per minute and how much blood is pumped in each beat, gives you the total amount of blood pumped each minute. Off to the right, I've shown you another abbreviation for heart rate, cardiac frequency. As science is using abbreviations, trying to standardize abbreviations. This is a frequency. How frequently does your heart beat? So correctly, we should talk about F subscript C, but in most exercise work, and certainly in exercise prescription and in the public, you'll see HR for heart rate. And that's what I will mostly use in these lectures. But you should be familiar with CO and QC for cardiac output, HR and F subscript C for heart rate. When the heart contracts and squeezes blood out, it does not completely empty. It does not squeeze out all the blood that's in it. Some is left in the heart after it contracts. And this next relationship explains that. Just as a reminder or a review, when the heart contracts, that is called systole. S-Y-S-T-O-L-E, systole. And you may be more familiar with the term systolic, as in systolic blood pressure. That's the pressure measured in the arteries right after the heart contracts. So systole is the contraction, the emptying, although it's not complete emptying, the emptying of the heart. Diastole, D-I-A-S-T-O-L-E, diastole, as in the diastolic blood pressure, is the period of time when the heart is relaxed and when it is filling with blood. So the heart empties in systole, fills in diastole. So the stroke volume, how much blood is pumped out, is the difference between the amount of blood in the heart after it fills and the amount of blood left in the heart after it contracts. Now look at the equation. Stroke volume, the amount of blood pumped with each beat, is the difference between the end diastolic volume, the volume of blood in the heart at the end of diastole, at the end of the filling period, the difference between that and the end systolic volume, the amount of blood still left in the heart after it contracts, after systole. Now, for most healthy people and for athletes, it really isn't a problem. During exercise, you shall see the end diastolic volume increases. You actually fill the heart a little more. and the end systolic volume is a little smaller. Your heart beats more forcefully, so it squeezes more of the blood out. So less is left in the heart. There's more in it to start with, less in it after systole, so the stroke volume will go up in exercise. And this is something we don't even worry about in healthy people and in athletes. If you're going to go into cardiac rehab, then you will find that you are concerned with measuring and evaluating and improving the two components of stroke volume, end diastolic volume and systolic volume. And certainly the medications that might be prescribed will be focused on one or both of these factors. If you're into fitness and sports, you don't even worry about it. Stroke volume, all you're going to worry about is what happens to the stroke volume during exercise. If you're in cardiac rehab, you worry about how are these changes to stroke volume made, because they may not occur normally in people with heart disease. All right, now we're going to get to what looks like just a bunch of numbers, but really, yes, you have to know the numbers, but what's more important is the concept. What is happening in exercise? What is happening with training? Yes, you have to know the numbers, but if you understand the concepts, and they're very logical, then it's much easier to learn and memorize, if you will, the numbers. Let's now look at a typical person, a typical male probably, at rest. And the values here correspond to the equation in the second bullet. Cardiac output equals heart rate times stroke volume. So this first line of data, at rest, typical cardiac output, 5 liters of blood per minute. Now that says 5 L times, there's a dot there, a raised dot, minute to the minus 1. If you are more comfortable writing this as 5 L, and you can use a capital L, slash minute, L slash minute is the same as this liter dot minute to the minus 1. 5 liters per minute. So in your notes, in your mind, if you want to write 5 L slash minute, that is fine. And honestly, often using a capital L, which actually may be technically correct, it depends where you're at and what journal you're working with. Capital L may not simply be more correct. It may be easier in your note-taking to see a capital L and know that that stands for liters, because I know when you look at that little L there, you might be seeing something other than a capital L, liters. Okay, resting cardiac output, 5 liters per minute. Oh, by the way, do you know how many fingers a person typically has on one hand? 5. Do you know how many liters of blood a typical person has? 5. We're just giving away these answers. Okay, 5 liters per minute. When in doubt, look at your hand. 5 liters per minute. Next number, heart rate, resting heart rate, 70 beats per minute or 72 beats per minute. These are just typical values for the average person. And you're going to say, but my heart rate isn't 70 beats per minute, it's 50. Well, you're not normal. You're a fit kinesiology major. These are values for a typical person. 5 liters per minute, 70 beats per minute, and the stroke volume, how would you know that on an exam? Take your pulse. 70 beats per minute. The next number, stroke volume, resting stroke volume, approximately 75 milliliters per beat. And again, if you want to write ml/beat, fine, milliliters per beat. Now, if you look at those numbers and you say 70 times 75, that's not 5, that's more like 5,000. Well, look at your units. The beats and the per beat cancel, so the units on the right-hand side are milliliters per minute. 5,000 milliliters per minute equals 5 liters per minute. So there's our first numbers, which we will memorize. Cardiac output at rest, 5 liters per minute, product of heart rate of 70, stroke volume of 75. Next line is maximal values or maximal exercise values. Before we look at the numbers, let's just stop and think for a minute. Cardiac output. We're pumping blood. This is how much blood we pump per minute. If we're talking exercise, would we expect our cardiac output to go up? Yes. Why? Because the blood carries oxygen to the muscles, carbon dioxide from the muscles, heat from the muscles, and it also carries waste products, and it carries fuel, and it carries hormones, all sorts of things. We'll focus mostly on the oxygen, and that's in fact what our next lecture is all about. But suffice to say, in exercise, we need to deliver more oxygen. We need to deliver more of a lot of things. We need to deliver more oxygen, so we want our cardiac output to go up. Does it? Yes. In a typical person, the cardiac output can go from 5 liters per minute at rest to 25 liters per minute in exercise at its highest, 25 liters per minute. How much of an increase is that? 5-fold. Another 5. A 5-fold increase. So we can pump 5 times as much blood during exercise. How do we accomplish this? First, we increase our heart rate. Second, we increase our stroke volume. You know that when you exercise, your heart rate goes up. And not only does your heart beat faster, it beats more forcefully. So it pushes out more blood, it empties more completely, so your stroke volume is higher. Now we'll put some numbers to this. Your heart rate can go from 70, in a typical person, from 70 to 200 beats per minute. It's almost a 3-fold increase. And your stroke volume can go from 75 to 125 milliliters per beat, almost doubling. So with a combination of increases in heart rate and stroke volume, you get your increase in cardiac output. Now, yes, it's easiest to memorize these 6 numbers. However, you could, or if you forget some, the cardiac output, 5 liters, 5 times higher in exercise, 25 liters per minute, that you pretty much want to memorize. Heart rate, you can take at rest, and you probably have an idea, you've probably heard, that your maximal heart rate is something like 220 minus your age. It's not the best predictor in the world, but on average, it's accurate on average. It's just not accurate for an individual. And since most of you are around 20 years old, 220 minus 20, 200 beats per minute, or you can just memorize, learn that for an average young 20-year-old, maximal heart rate is about 200. And then you could do the math and just calculate what the stroke volume must be by dividing 5,000 milliliters by 70 or 25,000 milliliters by 200. So what do we see here? In exercise, cardiac output increases because of increases in heart rate and stroke volume. Now those are maximal exercise values. If I asked you what happens in submaximal exercise, moderate intensity exercise, jogging, well, then your cardiac output might increase from 5 liters per minute to 10 liters per minute. Your heart rate might go from 70 to 120, and your stroke volume might go from 75 to, now I'm trying to do math in my head, to 100. You would get modest increases in both. If you were doing something that increased your cardiac output up to 20 liters per minute, you would find that your stroke volume was probably maxed out at 125, and your heart rate was responsible for the rest of the increase. But we will only worry about numbers at rest and in maximal exercise. Now, though that is the effect of exercise, now we're going to look at the effect of training. And as a reminder, exercise, one bout of physical activity. Training, repeated bouts of physical activity. When we talk about training and the effects on cardiac output and heart rate and stroke volume, we have to clarify. Do we mean the effect of training on the resting value, or do we mean the effect of training on the maximal, on the exercise value? So now we're just, or at first, we're going to look at the effect of training on the maximal values. Okay. It should make sense. If every day I go out and run and I pump blood carrying oxygen to my muscles, and every day my muscles say, gosh, we would like to have more oxygen. Wouldn't it be nice if you could pump more blood? It should make sense that we would be able to increase our maximal cardiac output, and indeed we do. A trained athlete can pump 35 liters of blood per minute, as compared to 25 for an untrained person. So there is an effect of training on an exercise value. How do we achieve, or how does the athlete achieve this greater maximal cardiac output? Is it because their heart can beat faster? No. Maximal heart rate, 200 beats per minute, unchanged. How then is the heart able to pump more blood? Stroke volume. Maximal stroke volume is greater. Now, the heart is a muscle. When you train a muscle, it gets stronger. So it can pump more forcefully. It can empty more forcefully. So if you look at that stroke volume equals end diastolic volume minus end systolic volume, it pumps more forcefully. So ESV will be smaller, so stroke volume is bigger. Something else also happens with endurance training. The inside of the heart becomes bigger. Now, we attribute this to we call it the preload of blood. In your training, you're pumping blood away from the heart, which means more blood is coming to the heart. So the blood comes into the heart, forcefully into the heart, and if you will, it stretches it. And the heart adapts over time to this constant being stretched more by becoming bigger. So now you have a heart that's bigger on the inside, it can hold more blood, and it's stronger. The walls of the heart are stronger, so it can fill more, so your end diastolic volume is greater, and because the muscle is stronger, it can empty more fully. So your stroke volume increases during maximal exercise. And it is the fact that your heart is bigger and stronger that explains the effect of training on maximal cardiac output. Now, let's look at this trained individual at rest. What do you think is the effect of training on the resting cardiac output? In an untrained person, it's 5 liters per minute. What do you think it is in an endurance athlete? Well, the answer is no change, 5 liters per minute. Now, please don't use the word efficient when you're thinking about this. After training, a person sits there at rest. They need to deliver some oxygen to their muscles. They have to pump some blood to their muscles, and they have to pump just as much blood when they're fit as before they were fit. So that value for resting cardiac output after training is 5 liters per minute. What is affected by training? Okay, you can go ahead right now and write in 50 beats per minute for the resting heart rate. And then if you do that, you're going to say, well, stroke volume at rest must be 100 milliliters per beat. So now you've got the numbers. 5 liters per minute, 50 beats per minute, 100 milliliters per beat. Now, what is the effect of training? We've already talked about it. What is the effect of training on the heart? It gets bigger and stronger. It fills more. It empties more forcefully. The effect of training on the heart at rest is to increase the stroke volume. If the stroke volume is higher, then the heart rate can be, is permitted to be, consequently is, lower. Now, because we can measure heart rate, we like to say, oh, training causes a lower heart rate. Well, that's not wrong, but what training causes is a higher resting stroke volume. Consequently, we have a lower resting heart rate. Now, I don't even have a line for it here, but if we were talking about exercising at a given intensity, it could be I'm going out for a 10-minute per mile run, or a 6-minute per kilometer run, or I'm riding my bike at level 4. Before and after training, in a fit person versus an unfit person, what is the effect on cardiac output? None. It takes just as much blood, takes just as much oxygen to run this certain pace after training as before. You may, again, your heart is bigger and stronger, so you'll have a larger stroke volume at any given work rate and consequently a lower heart rate. Now, I'm not going to give a whole bunch of examples of submaximal exercise intensities, but the important thing to remember is, regardless of whether you're at rest, at some submaximal exercise intensity, or at max, the effect of training is on the stroke volume. And then consequently, we'll see differences in heart rate at rest and heart rate at any given submaximal work rate. Your maximal heart rate is always going to be your maximal heart rate. And having said that your maximal heart rate is always going to be your maximal heart rate, you might have two questions. And the first would be, why doesn't your maximal heart rate go up? You just look at that line 3, that equation. Wouldn't it be great if we could multiply 175 milliliters per beat by 300 beats per minute? Well, mathematically, yes, that would be very nice. But physiologically, when your heart is beating 200 beats per minute, it has what? About 1/3 of a second to fill. Well, it can barely fill in 1/3 of a second. And actually, it has 1/6 of a second to fill and 1/6 of a second to empty. If you beat any faster than 200, it doesn't have time to fill. If it doesn't have time to fill, then your stroke volume would suffer. So if your heart could beat 300 beats per minute, your stroke volume would be 50. And that's a losing proposition. So even with no increase in maximal heart rate, it's okay, because that permits you to have enough time to fill the heart, to fill your bigger, stronger heart with blood. And not to confuse the issue, if anything, with training, your maximal heart rate may go down. A highly trained individual, 20-year-old, might actually have a maximal heart rate 10 beats lower than they did before they were fit. Now you're going to look at the math and say, boy, that really doesn't make sense. But yes, it does make sense to lose a little bit in terms of maximal heart rate if you can gain it in terms of maximal stroke volume. Bottom line here, endurance training, bigger, stronger heart. Bigger on the inside so it can fill more, stronger so it can empty more fully. All right, those were some numbers about what does happen. Now we'll talk briefly about what makes it happen. What makes your heart rate increase during exercise? What makes your stroke volume increase during exercise? And it is largely under neural control. Now, if you remember back to biology, the autonomic nervous system has the parasympathetic and sympathetic branches. The autonomic nervous system controls your heart rate. Sympathetic, the fight or flight. When there's more sympathetic, your heart beats faster. Parasympathetic, on the other hand, it causes the opposite effect. It causes a slowing of the heart rate. I like to think of this as the sympathetic is the gas pedal and the parasympathetic is the brake. And as you sit here listening to this lecture, when you're at rest, you actually have input from both the sympathetic and parasympathetic. If you will, you're driving with your foot on the gas and your foot on the brake. I wouldn't recommend this for your car, but it makes a lot of sense for your heart. Now, when you start to exercise, you're now able to do two things to increase your heart rate. You take your foot off the brake, you push your foot on the gas. So you withdraw parasympathetic activity and you increase the sympathetic activity. Now, I've said here that the withdrawal of the parasympathetic is important mostly at the onset of exercise and at low intensities. And let me hope I can explain that with this little graph here I've drawn. What that shows you is over time, a person, this is the person's heart rate you're looking at here, and I make them exercise so their heart rate goes from 100 to 140. And then I increase the resistance, or I make the treadmill go steeper or whatever, and their heart rate goes from 140 to 180. So their heart rate went from 100 to 140 and 140 to 180. Now, the way I've drawn it here isn't correct. It shows you that it takes the same amount of time to go from 100 to 140 as it does from 140 to 180. Okay. In fact, one of those increases occurs faster. I abruptly change the work rate. One of those increases goes faster. Which do you believe occurs faster? 100 to 140 or 140 to 180? If you said 140 to 180 is faster, you probably felt that the reason for that is because you're already warmed up. Well, that's not the case. In fact, it takes longer to go from 140 to 180 than it does from 100 to 140. Here's why. To go from 100 to 140, you withdraw your parasympathetic, you take your foot off the brake, and you push on the gas. Well, when you're at 140, you've already taken your foot off the brake. So to go from 140 to 180, all you can do is put your foot on the gas. So now you only have one thing driving the increase, So it must happen more slowly. If you imagined what your heart rate looks like, how it increases if I just gave you the big workload all at once. So it went from 100 to 180. You know it would increase very rapidly and then kind of level off. So you can see very clearly if you're jumping from 100 to 180, then the part that going from 100 to 140 occurs much faster than 140 to 180. Now that's not exactly the same as going from 100 to 140 and then changing the workload and going from 140 to 180, but it does give you something of an idea of how the heart rate increases over time when challenged with different exercise intensities. And you should remember the role of sympathetic and parasympathetic. And certainly if you're in cardiac rehab, you're going to be dealing with medications that affect the parasympathetic and the sympathetic correctly. Some medications affect the sympathetic, some affect the parasympathetic. Now, what causes an increase in stroke volume? I'm just going back to heart rate for a second. You know that the heart rate is mediated by the SA node, sinoatrial node. That if you took the heart out of the body, now maybe you did this in high school biology, you took a frog's heart out, and if you're sitting there cringing going, oh, that's a horrible thing to do, that's disgusting, okay, maybe you didn't do that. Maybe you've seen the movie where the guy reaches into the other guy's heart and rips his heart out and it keeps beating and beating and beating. Okay, that's not gross. Okay, the heart is beating even though it's not connected to the nervous system. It has its own little pacemaker. And that pacemaker sets its own pace, and that pace is moderated by the sympathetic and the parasympathetic. Okay, what determines how forcefully the heart beats? You've got this muscle, and the only thing that changes how forcefully it beats is sympathetic activity, because parasympathetic nerves don't synapse with, don't affect the heart muscle itself. Only the sympathetic branch does. So the only way to make your heart increase the force of contraction and therefore the stroke volume is by increasing sympathetic activity. And of course, this does occur in exercise. Now, this next item may be a little confusing. During exercise, I withdraw parasympathetic activity. That has no direct effect on the stroke volume because the parasympathetic doesn't activate the heart muscle. But when I withdraw the parasympathetic, what effect does that have? It increases the heart rate, which increases the cardiac output, which increases or affects the amount of blood coming back to the heart. So the heart fills more. If it fills more, then the heart muscle is being stretched. Okay, now just whether or not it's caused by parasympathetic activity. When the heart is in diastole and blood is coming into it, it stretches the heart muscle. A stretched muscle contracts more forcefully. Remember our lectures on muscle. So the more blood that is being pumped away from the heart, then the more blood is coming back to the heart, and the more blood comes back to the heart, the more it stretches the heart muscle, the more forcefully it pumps. Now this is called the Frank-Starling mechanism. In the heart, the fact that a stretched muscle contracts more forcefully is called the Frank-Starling mechanism. Now basically what I've just said is the more blood you pump from the heart, the more forcefully the heart pumps, so it pumps more blood. And you're going to sit there and go, well, that's kind of circular logic. Well, it is kind of circular logic, but what it means is a lot of what drives the heart to pump more forcefully is automatic. It's because the heart is pumping that it pumps more forcefully. Because it's pumping more, it pumps more forcefully. It doesn't need to get information from the brain. And this really only becomes important when, like many things, you only value this Frank-Starling mechanism when it's taken away. So we'll give you an example when the Frank-Starling mechanism is taken away and where stroke volume can be affected by something other than sympathetic activity. But the bottom line on this slide is, what causes an increase in heart rate? Reducing the parasympathetic, taking your foot off the brake, increasing the sympathetic, pushing on the gas. What increases the stroke volume? Sympathetic activity. But we always have to remember that the Frank-Starling mechanism plays a role in maintaining an adequate emptying of the heart. So, we have discussed the effects of exercise on cardiovascular responses: heart rate or cardiac frequency, stroke volume, and cardiac output. And we've also discussed the effects of training on resting values and on exercise values. And when we talk about exercise, we may talk about a fixed submaximal intensity, jogging at a certain pace, and we also talk about maximal responses. And in maximal responses, after training, you're going to have to run faster or work at a higher work rate than you did before training. So sometimes we talk about a fixed submaximal intensity, a fixed intensity, but with maximal responses, we're just saying, hey, what can your cardiovascular system do? We know it may take a greater work rate to elicit this response, but what can the cardiovascular system do? What's your maximal heart rate? What's your maximal stroke volume? What's your maximal cardiac output? And then we talked just a little bit about cardiovascular control and the importance of the sympathetic and parasympathetic nervous systems. So that is part one of the cardiovascular system. 2 more parts to go.